Welcome you all. On this lecture, I will explain about how to solve the numericals on centrifugal pumps. So here, problem number 1. A centrifugal pump works against a head of 30 meter and discharge is 0.25 meter cube per second while running at 1000 rpm. The velocity of flow at the outlet is 3 meter per second and the vane angle at outlet is 30 degree. Determine the diameter and width of the impeller at outlet if the hydraulic efficiency is 0.8. So first of all, by reading this numerical, try to write the given data here. A centrifugal pump works against a head of 30 meter. That means manometric head in a centrifugal pump is 30 meter and discharge, that denoted by Q, is equals to 0.25 meter cube per second, and speed is given as N is equals to 1000 rpm. The velocity of flow at outlet is 3 meter per second. That means VF1, VF2, that is outlet means that is exit. The VF2 is equals to 3 meter per second and vane angle at outlet, that is our vane angle or blade angle at outlet is beta 2 is equals to 30 degree. So in this given data, calculate what is the diameter as well as width of the impeller at outlet if the hydraulic efficiency is 80% or 0. Meter H is equals to 0.8. So now these are the given data here. Yes, H of M, there is a manometric head is equals to 30 meter, discharge is Q is equals to 0.25 meter cube per second, N is equals to 1000 rpm, VF2 is equals to 3 meter per second, beta 2 is equals to 30 degree. Now what about the diameter at outlet? There is a D2 as well as the width of the impeller at outlet, that is a B2, and manometric efficiency is given as 0.8. So now draw the velocity triangle at outlet as well as exit of the centrifugal pump. So in inlet, that is flow is radial. So for that reason, that is a V1 is equals to VF1, that means alpha 1 is equals to 90 degree. And at exit, that is a velocity triangle is given as shown in figure. So this is a velocity triangle for this one, inlet as well as outlet conditions. So from outlet velocity triangle, so now from the trigonometric relations, the tan beta 2 is equals to VF2 by U2 minus VU2. So this relation is taken from the exit velocity triangle. So according to that, tan beta 2 is equals to VF2 by U2 minus VU2. So now here we know the value of beta 2, there is a blade angle is given and VF2 is given, and U2 as well as VU2, these are the two unknowns here. So for that reason, the tan 30, the beta 2 angle is 30 degree, and VF2, that is the flow velocity at exit, is given as 3 meter per second. U2 as well as VU2 are the two unknowns. So now you are getting one expression, U2 minus VU2 is equals to 5.2. So that is equals to, so now it is that is expressed in terms of what, U2. The U2 is equals to 5.2 plus VU2. So that is expression number 1. The manometric efficiency or hydraulic efficiency of the pump is given by the expression, the neta manometric is equals to manometric head into to the ratio of VU2 into U2 by G. Now substitute the values here. The manometric efficiency is given as 0.8. Manometric head is 30. The VU2 value is unknown, and U2. So we already got an expression for U2. The U2 is taken as 5.2 plus VU2. So that is substituted in this expression. So instead of U2, substitute 5.2 plus VU2, and G value is acceleration due to gravity is 9.81. The after simplification of this expression, so now we are getting the value of VU2. VU2 in terms of expression as a 5.2 VU2 plus VU2 square is equals to 367.88, and this one you can write that expression as VU2 square plus 5.2 VU2 minus 367.88 is equals to 0. So now this expression gets solved by using the relations or by using the expression, that is a quadratic expression. So that is VU2 is equals to, so that this one is taken as the x value is equals to minus b plus or minus square root of b square minus 4ac by 2a. So according to that, in this previous expression, that value of b is equals to 5.2, and then a value is equals to 1, and c value is equals to minus 367.88. So that is actually, that is in form of ax square plus bx plus c is equals to 0. From this, for that the quadratic equation, so now VU2 is equals to minus 5.2 plus or minus square root of b square, that is 5.2 square minus 4, there is a value is equals to 1 and c value is equals to minus 367.88 divided by 2 into a, that is 2 into 1. So by solving that expression, we are getting the value of VU2 as 16.75 meter per second. So now from equation number 1, the previous expression what you explained in that previous slide, that is a U2 is equals to 5.2 plus VU2. So now we got the value of VU2 here. So now substitute the value of VU2 in that U2 expression. So now you are getting the value of U2 value. The U2 is equals to 5.2 plus VU2. So now U2 is equals to 5.2 plus the value of VU2 is equals to 16.75. That means now U2 value is equals to 21.96 meter per second. So now find out what is the diameter of the impeller at the outlet. So now that is calculated by using the expression U2 is equals to pi d2n by 60. We know the value of U2 as 21.96. The diameter is unknown, we need to calculate now, and speed is given as 1000 rpm. Hence now d2 is equals to 0.419 meter. So what about the width of the impeller at outlet? The width of the impeller at outlet is calculated by using the discharge formula. The discharge is equals to area of the flow into velocity of flow. The area of the flow is calculated by using that is equals to pi d2 into b2. So here discharge is known, that value is 0.255, and d2 value is already calculated, that is 0.419. B2, the width of the impeller we need to calculate, and velocity of the flow is given as 3 meter per second. By substituting these values in this discharge formula, now we will get the answer for the width of the impeller at outlet B2 as 0.0632 meter. So that is a solution for the first numerical on centrifugal pump. So move on to the second numerical. There is problem number 2. A centrifugal pump discharges 0.15 meter cube per second of water against a head of 12.5 meter. Speed of impeller is 600 rpm. The outer and inner diameter of impeller are 500 mm and 250 mm respectively, and the vanes are bent back at 35 degree to the tangent at exit If the area of the flow remains 0.07 meter square from inlet to outlet, find first one manometric efficiency of the pump, second one is a vane angle at inlet, loss of head at inlet to impeller when discharge is reduced by 40% without changing the speed. So this is the given problem. So now list out the given data. A centrifugal pump discharges 0.15 meter cube per second of water. That means Q is given as 0.15 meter cube per second of water against the head of 12.5 meter. That is manometric head on this centrifugal pump is 12.5. Speed of the impeller is 600 rpm, that is N is equals to 600 rpm. The outer and inner diameter of the impeller are, the outer diameter is 500 millimeter and inner diameter is 250 millimeter respectively. That here outer diameter is denoted by the letter D2 and inner diameter is denoted by the letter D1. And vanes are bent back at 35 degree to the tangent at exit. That means now blade angle at exit, that is a beta 2 angle at exit is 35 degree. If the area of the flow remains that is a constant from inlet to outlet, that is 0.07 meters square, then A is equals to 0.07 meters square. So in this problem, first of all, calculate what is the manometric efficiency of the pump, that is a newton manometric. Second one is vane angle at inlet, that is vane angle at inlet means beta 1 is how much. And third part here it is loss of head at inlet of impeller when discharge is reduced by 40%. So now what is the loss of head occurs at the inlet of the impeller? So when 40% of its discharge is reduced from the initial condition without changing the speed, that is the speed remains constant, that is what N is equals to 600 rpm, but discharges get reduced for 40% from the initial condition. So for this reduction in discharge, so what is the loss of head at inlet? So now given data here, the Q1 is given, that for the first condition initially the discharge is 0.15 meter cube per second, manometric head is given as 12.5 meter, the speed is equals to N is equals to 600 rpm, the D2 outer diameter is given as 0.5 meter, D1 is equals to 0.25 meter, beta to blade angle at outlet is given as 35 degree, the area of the flow A is equals to 0.07 meter square. So now find out what is the manometric efficiency. Second thing is what, calculate the blade angle at inlet and also calculate the loss of head at inlet of the impeller. For this condition, this is a velocity triangle. So once again at the inlet, that is a radial inlet, that means V1 is equals to Vf1 and alpha 1 is equals to 90 degree. So by referring this velocity triangle, you have to calculate the required data in order to calculate the volumetric efficiency, that is manometric efficiency, as well as to find out the blade angle at inlet beta 1. So initially calculate what is the U2 value. The U2 value is calculated by using the formula pi d2n by 60. So here diameter value is known and speed of the impeller is known, there is a centrifugal pump is known, that is 600 rpm. By using that we can find the value of U2, so that is equals to 15.7 meter per second. Similar manner we have to calculate what is the value of U1, that is at inlet, there is a pi d1 n by 60. So once again at the diameter at inlet is 0.25 meter, speed remains constant, that is 600 rpm. So now U1 is equals to 7.85 meter per second. So here the flow remains constant, the flow velocity remains constant from the inlet to the outlet, that is Vf1 is equals to Vf2. Such that is calculated by the expression from the discharge. The discharge is equals to area of the flow into velocity of the flow. So by that the velocity of the flow is equals to the ratio of discharge to area of flow. So here the VF1, the flow velocity at inlet is equals to flow velocity at outlet is equals to the discharge is given, that is 0.15 meter cube per second, and area is given as 0.07 meter square. By this values we will get the flow velocity is constant from the inlet to the outlet of the centrifugal pump, and that value is 2.14 meter per second. Next, calculate manometric efficiency. The manometric efficiency, in order to calculate manometric efficiency, we need to calculate the value of VU2 here. So that VU2 value is calculated by using by referring some trigonometric relations with that velocity triangles, that is tan beta 2 is equals to Vf2 by U2 minus Vu2. So here the blade angle is given as 35 degree and velocity of the flow is 2.14 and U2 value is 15.7. Now Vu2 is equals to, so by simplifying this one we will get the Vu2 value is 12.64 meter per second. So now manometric efficiency is equals to the manometric head HM to the ratio of VU2 into U2 by G. The substituting the values over here, that is the HM manometric head is equals to 12.5 and VU2 value is equals to 12.64 into U2 value is equals to 13.7 and G value is equals to 9.81. So by referring that, there is a manometric efficiency is equals to 0.6181, and that means in percentage it is 61.81%. So what about the vane angle at inlet? That is, what about the value of beta 1 at inlet? So that is calculated by using the trigonometric relations, that is tan beta 1 is equals to Vf1 by U1. So now we know the value of Vf1 as well as U1 here and substituted here, and beta 1 angle is, or blade angle at inlet or vane angle at inlet is equals to 15.21 degree. The next third part of the numerical is that the loss of head at inlet due to 40% reduction in discharge. So now what about the new discharge here? So initially discharge Q1 is equals to 0.15 meter cube per second. So because of 40% of the discharge, the new discharge value is calculated here. So once again, if the discharge is directly proportional to area as well as velocity of the flow. So here the area of the flow remains constant, that is 0.07 meter square. So in turn the discharge now totally directly proportional toward the velocity of the flow. In case the discharge is reduced from the first case to the second one, so automatically it indicates what there is a drop in velocity of the flow also. That is the velocity of the flow will also reduce at inlet, that is a Vf1 will reduce. So with respect to that, so here when the discharge is reduced by 40%, the new velocity of the flow is shown in figure. So now this is a new velocity triangle. So here Vf1 that indicates the initial velocity of the flow. So that when Q1 is equals to 0.15 meter cube per second. So now velocity is here discharge is reduced by 40%. So for that reason the new velocity of the flow, that is a Vf1 dash. The Vf1 dash is indicated in this velocity triangle. So that will also cause the reduction in what? Vu1 dash. Correct, Vu1 dash. So that is a velocity triangle for the first condition as well as the second condition by the 40% of the reduction in discharge. Now what is the new velocity of the flow? The Vf1 dash is equals to, so initially it is taken as 100%, that is 1 minus the 40% of the reduction will occur here. For that reason it is 0.4 into times of what? Initial flow of velocity. Flow velocity, there is a Vf1. That means the new velocity of flow, there is a Vf1 dash is equals to 1.28 meter per second. So now loss of head at inlet to the impeller is calculated by using the expression u1 minus u1 dash whole square by 2g. So here u1 represents the initial uh, velocity and u1 dash represents what the new velocity. There is divided by 2g. So now here after substituting the values here by taking the relations u1 dash is equals to vr1 dash cot beta 1 is equals to the vr1 value is equals to here the vf1, there is a vf1 cot beta 1, there is a value of vf1 is equals to 1.284, the cot beta 1 angle is a 15.21. So for that reason the u1 dash is equals to 4.72 meter per second. So now therefore the loss of head at inlet is calculated as, that is the u1 is equals to 7.85 and u1 dash value is equals to 4.72. The whole square of that one divided by 2 into 9.81. That means the now loss of head occurs of 0.5 meters. So when compared to the initial stage, now 0.5 meters of manometric head is get reduced by the 40% of the reduction in discharge. So this is a solution for this second numerical on centrifugal pump. Coming to the third numerical. The third numerical is a centrifugal pump working in 1565 liter per second against a mean lift of 6.1 meter when the impeller rotates at 200 rpm. The impeller diameter is 122 centimeter and area at outlet periphery is 6450 centimeter square. If the vanes are set back at an angle of 26 degree at the outlet, find hydraulic efficiency. Second one, power required to drive the pump. Third one, and if the ratio of external to the internal diameter is 2, find minimum speed to start pumping. So this is the third numerical related to centrifugal pump. So according to this one, list out the given data here. A centrifugal pump working in 1565 liter per second, that is a discharge Q is equals to 1565 liters per second. So now convert that into SI unit, there is a meter cube per second by multiplying with this value with the 10 to the power minus 3 and a mean lift of 6.1 meter. There is a manometric head is given as 6.1 meter and impeller rotates as 200 rpm. So here N is equals to 200 rpm. The impeller diameter is 122 centimeter and area at outlet, the outlet area is given, periphery outlet area is given as 6450 centimeter square. If the vanes are set back at an angle of 26 degree at the outlet, there is a beta 2 is equals to 26 degree. So now calculate what is hydraulic efficiency and what is the power required to drive the pump. Okay. And third part is to find out what is the minimum starting speed when the ratio of external to internal diameter is 2. The external diameter is given by D2 and internal diameter is equals to D1. That means the external diameter is equals to 2 times of the internal diameter. So now the given data is like that. Q is equals to 1565 liter per second, that is equals to 1.565 meter cube per second. Manometric head is equals to 6.1 meter. Speed N is equals to 200 rpm. D2 is equals to 122 centimeter. The area at outlet is given as 6450 centimeter square. Beta 2 is equals to 26 degree. D2 by D1 is equals to 2. This ratio of external diameter to internal diameter is equals to 2. So we need to calculate what is the manometric efficiency and what is the power required to drive the impeller, and third one is what is the minimum starting speed. So this is the velocity triangle at inlet as well as the outlet of the centrifugal pump for these given conditions. So now U2 is equals to pi D2 n by 60. So here outer diameter is given, that is 122 centimeter, that means 1.22 meter, that is U2 is equals to 12.77 meter. And discharge, from the discharge formula, the discharge is equals to pi D2 V2 into Vf2. So that is equals to the pi D2 V2 is equals to area of flow into Vf2, that is the velocity of flow. So now discharge is given and area is also given. Actually area is given in centimeter square, convert that into meter square, and the velocity of the flow is unknown, there is a Vf2, and Vf2 is equals to 2.43 meter per second. So now hydraulic efficiency or manometric efficiency. So from the outlet velocity triangle, the tan beta 2 is equals to Vf2 by U2 minus Vu2. So here beta 2 angle is 26 degree. So that is equals to the velocity of the flow is 2.43 and U2 value is equals to 12.77 and U2 is unknown and U2 is calculated and that value is 7.79 meter per second. So now manometric efficiency is equals to manometric head to Vu2 into U2 by G. Substitute the values over here. There is a manometric head is given 6.1 and Vu2 value is 7.79. U2 is equals to 12.77 and G value is equals to 9.81. So now manometric efficiency is equals to 0.601 or 60%. Then what is the power required to drive the pump? The power required to drive the pump is calculated by using the formula. The power is equals to rho into Q, Vu2 into U2. So here rho into Q, that represents mass of the fluid. The mass of the fluid flowing through the centrifugal pump, that is rho into Q. Then Vu2 into U2 by 1000. So substituting the values here, there is the density of the water is 1000 and Q value is given as 1.565 into Vu2 value is calculated 7.79 into U2 is equals to 12.77 by 1000. So now we are getting the power required to drive the pump is 43.65 kilowatt. Next, what about the minimum starting speed? So in order to get the discharge, we need to run the centrifugal pump at a desired speed. So otherwise there is no flow will occur from the centrifugal pump. So now we have to calculate is what is the minimum speed is required to get the output or discharge from the centrifugal pump. So here by using the diameter relations, that is d2 by d1 is equals to 2, that means d1 is equals to d2 by 2, that is a half of diameter at inlet is equals to half of the diameter at exit. So now diameter at outlet is given by 1.22 by 2, that is the diameter at inlet is equals to 0.61 meter. Now manometric efficiency is calculated by using one relations, the minimum starting speed. The minimum starting speed of the centrifugal pump is calculated by using the standard expression. There's 120 into manometric efficiency into Vu2 into D2 by pi into D2 square minus D1 square. Now substituting these values here, that is 120 into the manometric efficiency is 60%, that is 0.601. and Vu2 value is equals to 7.79 and diameter at outlet is equals to 1.22 pi into diameter at outlet square, this is 1.22 square minus 0.61 square, there is a d1 value. So now we are getting the minimum starting speed is equals to 197.73 rpm. That means in order to get the discharge from a centrifugal pump, we need to run the pump at minimum speed of 197.73 rpm. So these are the four different types of the numericals on centrifugal pumps, and in next session, in next lecture, I will explain some more numericals on these centrifugal pumps. Thank you.